Hi, I'm Stella. I'm a lecturer in Engineering Alloys and Metallurgy at Imperial College London, and I'm here to introduce you to the wonderful world of high temperature materials.
I'm a lecturer in Engineering Alloys. I'm also a member of the IM3, the Institute of Materials, Minerals and Mining High Temperature Materials Committee. And today I'm going to be presenting to you some of the work that we do and why high temperature materials are an important thing to investigate. This presentation was put together with the help of the High Temperature Materials Committee, which has a lot of representatives from industry, from the likes of Special Metals and Siemens and Rolls-Royce and many other industries, and also with the help of the High Temperature Materials Committee and Dr. Diane Aston. Now, high temperature materials are extremely important because many new technologies need them. We are pushing the current materials to their absolute limits in many applications, and they are starting to fail, which means that it's very important for us to develop new materials for these applications. And one of the aspects of this is to kind of think about the requirements of each material in terms of, for industrial gas turbines for power generation, such as the one seen in the top corner, the Siemens one, or just, even wires for light bulbs or anything for planes or aerospace applications and many other applications. Now, high temperature materials are very widely used, especially in aerospace, aircraft, jet engines. Production of metals is very important, and in power generation. The properties that we look for in high temperature materials are, well, high melting point, something that was not going to burn, something that's going to resist oxidation, something that's going to stay strong even at high temperature, so at the operating temperature, and something generally with low thermal conductivity and low coefficient of thermal expansion. These are not always essential, but they do help for specific applications. Now, there are many different classes of materials that can operate well at high temperature. Some of them are ceramics, some of them are metals, and the ceramics tend to have the highest temperature capabilities. They have very highly directional bonding, so covalent bonding between the atoms. They have a very high compressive strength, but poor tensile strength. What that means is that when you pull them, they have more of a tendency to fail than if you were pushing on them. They also have low thermal conductivity and coefficient of thermal expansion. Whereas metals, the bonding is less directional. Metallic bonds are not as directional as covalent bonds and ceramics. That means they have good tensile strength and better ductility than ceramics, which is a very important thing for specific applications. And their properties can be changed and tailored to the applications by alloying, so by mixing different metals together. They have a higher thermal conductivity and a higher coefficient of thermal expansion, so pros and cons, and their temperature capability tends to be a bit more limited than the ceramics. Now, the materials used by temperature. Here we have on the left-hand side a thermometer, essentially going from 0 to 2000 degrees C, and next to it different varieties of alloys and ceramics that are used for specific applications. So the lowest temperature capability is things like aluminium alloys. They tend to not, they are used in cars or in things that require lightweight because they're lighter, but they tend to not be used in higher temperature applications because 200 degrees, absolute most 300 for some of them that are specifically alloyed, but they don't tend to have enough strength after these temperatures, and they melt at 600. So up until about 500, 550, it tends to be titanium alloys. The advantage is they're lightweight. And then also steels. Steels are heavier but cheaper, so it depends on the specific applications and the requirements. Now, nickel alloys are particularly interesting because they can operate up to very high temperatures. So in this case, they're used up to 1100 and beyond, as we will see later on. And then beyond that, we tend to need to use ceramics. Ceramics have the highest temperature applications, so things like silica and alumina. Now, if we were to pick a high temperature metal, one of the first things that we discussed before was we need to pick something with a high melting point. So what we have here is a graph of all of the metals on the periodic table and other elements as well, and their melting points. Now, they're in order as you would find them line by line on the periodic table. That's why it seems like a bit of a random order. But some elements have higher temperature capability than others. And by plotting their melting point versus the atomic number, we can figure out what we would want to use for specific applications. Now, the highest melting point is carbon, but carbon is diamond, and carbon has the tendency to burn in all other formats, so it's not really a good functional material. And tungsten also has a comparable, sort of similar melting point, but it's very rare and expensive, and so are molybdenum, niobium, the other the highest melting point materials available on the periodic table. Then there are things like vanadium and chromium, but they're not very good structural materials. Vanadium oxidizes very, very readily and produces very toxic oxides. Chromium is not a good structural material at all. It is used in alloys, but it's not used by itself, just because it's very brittle and difficult to work with by itself. Iron, cobalt, and nickel are the best choices. Titanium has a higher melting point, but it oxidizes very fast and it can burn, so it is used alloyed rather than as pure titanium, and it is more expensive. So if we look at iron, cobalt, and nickel, these tend to be the main structural metals that we use for this high temperature application. Now, there are different challenges for high temperature materials. Melting and burning are quite obvious. But also we look at creep and oxidation resistance, and I'm going to explain a little bit about what these are and how we counteract them. Now, creep is seen quite often in things like if you go in really, really old churches, you might see that the glass is a bit thicker at the bottom of the window than it is at the top. That's because slowly gravity has worked to change the shape of the material because under its own weight. And this happens if you hang a wire from the ceiling, it will gradually get longer over the years. And that's the general principle of creep. Metals elongate as soon as they are loaded, and this happens more at high temperature. At low temperature, you need to apply quite a lot of strain for it to happen. Whereas at high temperature, quite a lot of stress attaches a good weight for it to happen. Whereas at higher temperatures, it happens much, much quicker. And it can continue to happen until the load is removed. It can even happen under its own weight. So in this case, it tends to happen generally above 0.4 of the melting point of the material. Oxidation, I think everyone's come across the concept of oxidation as a reaction with oxygen as a loss of electrons. And a few metals oxidize, not all of them. A few noble metals, such as gold and platinum, do not react with oxygen even at high temperature. That's why they're extracted from the ground as gold or platinum, and that's why they're called noble metals, whereas most of the others do react with oxygen. So for example, nickel forms a nickel oxide. The rate of oxidation increases with increasing temperature, but the metal oxides can be a good protection for the metallic surface. So a lot of them, like aluminium forming alumina, they form very protective oxides. So once the surface is oxidized, it's passivated and it's no longer, well, the oxide still is going to grow a little bit, but mostly the damage will have slowed down quite a lot and the oxide will be protected. Some metals don't form protective oxides at all, things like iron, molybdenum, titanium, and that's why if they are required, they need to be alloyed with metals that do form protective oxides. And now I'm going to give a few examples of applications. of what we have learned of high temperature materials. So the main applications that I have in this presentation are jet engine turbine blades and thermal barrier coatings, but also failure of steam generators and high temperature ceramics and materials for energy. But today we're going to focus primarily on jet engine turbine blades and turbine blade thermal barrier coating if we have time at the end. Turbine blades, they must operate under very extreme conditions, and I'm talking about temperature and I'm talking about stress. Each of these blades has to produce 1,000 horsepower, and these blades are found in jet engines, airplane engines, the kind of engines that you would find on any passenger aircraft that any one of you would have been on. Some airplanes are twin engines, they have 2 of them, some of them have more, but these engines operate under the same kind of principle. So at the very front of the engine, the larger blades, the ones that you see, are the fan blades. They're made of titanium and they suck all of the air in, and then that air is compressed. It's squeezed down in the compressor. Those blades in the compressor tend to be made out of titanium as well, until we reach the point where the fuel is burned. The fuel burns at about 2,000 degrees C, so it's very, very hot. And the first line of turbine blades after that, they're made of nickel alloys, and they are the hottest rotating part in the entire engine. So after the air is squeezed down in the compressor, the fuel is burnt at 2,000 degrees, and then it starts to expand and get pushed out of the back of the engine. So it spins the turbine, and the turbine is what spins the entire engine and how planes take off. It's the hot expanding gas that blows through the turbine, and it spins the whole engine. These blades, especially the first line of blades, they have to withstand really high temperature. Not quite 2,000 degrees. By the time the air gets to them, it tends to have cooled down, but maybe about 1,600. And they need to withstand up to 40 atmospheres, which is very, very difficult operating conditions. To reduce fuel consumption, we generally look for, better speed in plane engines, and that tends to push the engines to their extremes. They are getting hotter and hotter all the time to try and maximize efficiency, and that puts a huge strain on the material and on their properties. So new materials need to be developed regularly to fulfill the needs of the air engine market. Now, the first stage of the turbine, the one that I talked about, the one that has to withstand the hottest, harshest environment within the entire engine, is located right behind where the fuel is burned, and it's the hottest rotating part in the engine. It must cope with the most extreme environment. So here we will have some considerations of what to make them out of and why. Now, the high pressure turbine blades need to withstand, they need to operate at about 1,600 degrees C, which is quite interesting because it's 200 degrees above the alloy's own melting point. So if you've ever been on a plane and you can see the engine outside, each line of these blades inside the engine needs to be above its own melting point and still be strong and last. This is like putting an ice cube in the oven and expecting it to stay solid. It's a very difficult engineering challenge. And each blade, 200 degrees above its melting point, needs to produce 1,000 horsepower, which is the same output of a Formula 1 car. And the centrifugal load on each blade is equivalent to hanging a truck on the end of it. And these are about the size of my hand. These are, 20 centimeters long. And they need to generate 1,000 horsepower with a bus hanging, the weight of a bus hanging off the end of it, 200 degrees above its melting point, for 30,000 hours of operation. It's a huge challenge. I mean, how do you keep them solid? How do you keep them strong? Well, the material needs to be creep resistant. Like we said, it needs to not elongate, because as soon as they elongate, they're going to hit the casing as they spin. And they need to be strong, they need to be tough on impact. The engines ingest dirt and debris and birds and things. And they need to be oxidation and corrosion resistant, because you don't want them to fail. And they need to be stable for at least 3,000 flights or 30,000 hours. They also ideally would have low density, because they need to fly, and low cost. Now, this is a very difficult problem. Nickel alloys are called superalloys quite often because of their properties. They tend to maintain their properties up to very close to the melting point, which not all materials do. Most materials tend to start losing strength at much lower temperatures. Even half of their melting point is enough to lose strength. Ironically, ice is an example of a material that keeps its property up until the melting point. Nickel is another one. Nickel alloys are very, very carefully controlled. So we tend to pick elements off the periodic table and add them in the right amount, and they have been studied for so long in order to achieve the desired mix of properties. So nickel has a high melting point, which is a good start, but all these other elements like aluminium, titanium and tantalum, molybdenum, tungsten, rhenium, iron, boron, carbon, zirconium, chromium and aluminium are added for specific reasons. So we need to add some big heavy atoms to make it stronger. We need to add some things that produce the strengthening phase that I'll explain a bit more about later. And chromium and aluminium are added for protection. And then I'll also explain what grain boundaries are and why we need to strengthen them. The result is a very complex alloy that contains 10, 14 elements, each serving a very specific purpose. This microstructure, so it looks like this. If you look at the scale bar on this, it's 1 micron. To give you an idea, your average hair on top of your head is about 100 microns. Blonde hair tends to be sort of 80 microns. Darker hair tends to be maybe 100, 120. But this is, 100 times smaller than a human hair. And these little cubes, that is what the microstructure looks like. It forms these little cubes. They're made of 2 phases. The bricks, the cubes, they're called gamma prime, and the rest is called gamma. Gamma is nickel, just with a few added other elements to make it stronger. Gamma prime is a different phase, and it's a nickel aluminide. So nickel combines with aluminium to form these little cubes, these structures that give the materials strength. This is often called a brick and mortar microstructure. And I will explain a bit about how we tailor the microstructure and the grains. So all metals have a crystalline structure. Whenever we think of crystals, we think of beautiful crystals from the ground or in caves or in the Natural History Museum that are faceted and gemstones. We tend to think of that when we think of crystals, but metals, when they are liquid and you solidify them, they will solidify in a crystalline structure. So a metal consists of thousands of these crystals, and they will be oriented slightly differently. And as they solidify, these form, and they are oriented differently, and between 2 of them, there's a boundary. So each of these crystals is called a grain, and in between them, there is a boundary. And these can be bigger or smaller depending on how fast we solidify the material. And their properties tend to depend quite strongly on the grain structure. And that's why we add carbon, boron, zirconium to strengthen these boundaries. Now, turbine blades, like we said, they need to be up to 1600 degrees C and they need to be solid. And these grain boundaries tend to be a weak spot. Even after we've added these strengthening elements, they tend to be quite weak. And they tend to be the first thing to go when blades break. So this is why historically we found ways of eliminating them from the component, from the engineering part. So at the beginning, through processing improvements, at the beginning there were random crystal structures. So each blade had random grain orientations and a lot of weak spots. Then someone figured out that if you cool the melt from below, you can grow the grains upwards, and that's the second blade in. And you can see that in that case, the grain boundaries are still there, but there are none perpendicular to the blade. So none of them are in the preferred cracking direction, which removes one of the problems. Then people figured out how to make these a single crystal, like one grain. The entire thing is one grain, removing the grain boundaries, removing the weak points. And this change alone was sufficient to improve the temperature, the operating temperature of the blades up to 800 degrees. That's great, but it's half of what we need now. So through design improvements, once we reached the material's capability, the design came to the rescue, and cooling channels were built on the inside of each blade, and that's how they're cooled right now. So if you have a chocolate teapot, but you cool it from inside, you might expect it to stay solid. It's the same thing here. 1425 was the maximum temperature that was reached from internal cooling with these blades. Now we still needed more than that. So one of the things that is done these days is to coat them with ceramic. So they are cooled internally and they're coated. And that way the alloy can stay strong up to 1600 degrees and work at the selected operating temperature. So in summary, the constant drive for more efficient jet engines means that turbine blades and their materials must run hotter and hotter. The material must be strong, tough, creep and oxidation resistant up to high temperatures. Nickel alloys are the selected material for these applications, and since the 1940s, hundreds of different superalloys have been developed, many with very complex mixtures of elements. Today's turbine blades are single crystals, they're air-cooled, they're ceramic-coated, and they have the highest temperature capability. I would like to thank Diane Aston and the High Temperature Materials Committee for sharing these photos, and here are some of the companies that are part of the High Temperature Materials.
And there we have it. I hope you enjoyed this. If you have any questions for me, my Twitter handle is @StellaP12, so you can go and find me there or contact me through the college office. We'll hope to see you all next year. Bye.